My name is Hassan Azad, and this is my email. At sms.edu.pk. I need a class representative who can collect emails of the students, whoever wants to, because if you want, you can write to me your questions, and I've been experimenting with AI for past couple of years, so that I can tell you of the advantages and dangers of that. And many things which if you don't understand something, AI is really very helpful, but it makes a lot of mistakes. But that's a separate story. So, so what is this course about? What is this? Okay, so it is about solving PDEs of interest to physicists using group theory. So if you don't, I think yesterday somebody was telling me that he doesn't know even what a group is. How many of you know what a group is? Okay, just a couple. But don't bother. I'll tell you what it is. At the moment, you just have a rough idea of what I'm going to talk about. Okay. So, so the one of the main result of this is the following: the only second order operators of order 2 which are invariant under translations and SO3, the rotation group, and SO21, they are the Laplace operator d2 by dx2 plus d2 by dy2 plus d2 by dz2, and the other is this is for SO3 invariant and invariant under translations, and the wave operator. What's the symbol for wave operator? Box. How do you write the wave operator? Anyway, just write it. And the wave operator. D2 by dx2 plus d2 by dy2 minus d2 by dz2. So these are the only, which is quite a fantastic thing, I think. And Parvez will tell us why we see them all the time. Huh? But not right now, maybe later. Okay. So the main tools for this are linear algebra and advanced calculus. And looking at your tests, I saw that many of you do not have a clear idea about linear independence and dependence and about what it means for a space to be of dimension n. So therefore, I am going to start right from the beginning and I am going to revise some linear algebra. Okay. Minus. क्या क्या कह रहे हैं? किसमें? What is he saying?
He says, is that time? Yeah, it is time in relativity, but
because okay. अच्छा, you're saying whether it should be time. There's a variable x, y, and t.
But as in you need to tell them what SO3 is. It's
No, that I said to you, I cannot tell them right now. But at the end of the lecture, if they have enough time, I will tell them. This is just for you to focus on where we are heading. Okay. So if we have time, I will definitely tell you what is SO3 and what is SO21. That's real group theory, and it's not difficult at all, actually. So revision of linear algebra. I think so if I have a plane and I have a point P with coordinate xy, then you have the vector from O to P. And what are the components of this vector from O to P? They are xy. And Dr. Zeib has unfortunately used the brackets already, bra and cat, so I'm forced to use for the point xy the bracket also, the vector OP I will also write by xy. So OP is also xy. I don't want to use brackets because then it will confuse you. Okay, and if I have another point Q with coordinate uv, so how do you add the vector OP and OQ? By the parallelogram law of addition. And the vector, this actually turns out to be OP plus OQ is equal to x plus u and y plus v. And then you have the concept of scalar multiplication. Okay. So and now this is something which I like to call the basic theorem of linear algebra. एक तो चौक आप इससे कोई बेहतर क्वालिटी का चौक. This is top quality. Oh, okay. चलो ठीक. नहीं कोई कह रहा था Hogomo, he is going to gift us Hogomo chalks.
This is Jamil's talk, the chalk.
This one maybe, but not this one, right?
No, this one.
Achha, that's a difference. Okay. So this is yeah, this is vast. Any system of of k plus 1 homogeneous equations. Any system of k homogeneous equations. In k plus 1 variables has a non-trivial solution. Okay, so I'm going to prove it only for one equation and two equation, and then you will see all the terminology there also. So let's prove it for. So the idea of this proposition is contained entirely in what I'm going to discuss with you now, and this will be as a homework for you. Once you see what I do here, you will be able to prove this in general. So proof. Main idea is contained in the following two special cases. Number one equation in two variables. A1 x1 plus A2 x2 is equal to 0. So meaning of homogeneous means exactly this, and it's homogeneous any system of k plus 1 linear homogeneous equations. So linearity means that there is no higher power of x. Okay. So why does it have a non-trivial solution? If A1 and A2 are both 0, then
it's a trivial solution.
It has infinitely many. You can put any number you like and you will get it. If A1 and A2 are both 0, infinitely many solutions. Let's suppose that A1 is not 0. Then what do you get? So if A1 and A2 are both 0, x1, x2 can be arbitrary. Okay, so suppose A1 is not 0. Okay, so then I can solve for x1 in terms of x2. So x1 is equal to minus A2 over A1. And now you give me a non-trivial solution. No, give me one particular solution. Come on, it's staring at you. X1 is 1 and sorry, I made a mistake. X1 is equal to minus A2 over x2. Yeah, sorry, my mistake. So now x2 is 1 and x1 is minus. So x2 is equal to 1 and x1 is equal to minus A2 over A1. So this is a non-trivial solution, means that not all x1 and x2 are 0. Okay. Now let's do the same for two equations and three variables. So two equations This was case 1, case 2, two equations in 3 variables. And I am going to write it in such a way that you can do it your homework. So, it is A11 x1 plus A12 x2 plus A13 x3 is equal to 0. A21 x1 plus A22 x2 plus A23 x3 is equal to 0. This is a system of two linear homogeneous equations in 3 variables. So, now what will be the argument? Again, if all the coefficients a, I, j were 0, then any x1, x2 and x3 would be a solution. Let us suppose one of them is not 0. Without loss of generality, let us suppose that a11 is not 0. Okay? Then I can solve for x1 in terms of x2 and x3. And when you plug in here, you would get again a system of one equation in two unknowns, and by the previous one you can solve for it, and that is the proof. Okay? Okay? And this proof generalizes. So, let me write down the details. So, if all aij are 0, then any x1, x2, x3 would do, are solutions. Okay. So, suppose now suppose A11 is not 0. Then what do you get for x1? Then x1 is equal to minus A12 x2 minus A13 x3 divided by A11. Plug in the second equation. You get A21 times minus A12 x2 minus A13 x3 over A11 plus A22 plus A23 x3 is equal to 0. Now, what kind of equation is this? It's homogeneous or non-homogeneous? Huh? It's homogeneous and in two variables. So, by the previous case, it has a non-trivial solutions. So, this second, now this is an equation in two variables. In two variables. So it has a non-trivial solution. X2 x3 is equal to C2 C3 with one of C2 or C3 not 0, with one of so with this choice, and then x1, so then what will be x1? I'm right, it's obvious, but I'll write it down. So then x1 is minus A12 C2 minus A13 C3 divided by A11. Okay, and since we know that one of these C2 or C3 is not 0, we get that this is a non trivial solution. So now you will be able to do it as a homework by induction? Yes? Okay. So that will be okay. So now this has why do we say that the plane has two dimensions?
Because we need two independent variables to find any point to describe any
Hmm? That's right. But why can't you have? How do you know that you can't have three independent vectors?
So minimum two variables
you can
have to locate any point on this plane.
It's because exactly of this reason that you don't. I think we need to go over this carefully. Okay. So consequences. Any three vectors okay, before this I do vectors v1, v2, vk are linearly dependent if we have an equation, so x1 v1 plus x2 v2 plus xk vk is equal to 0 with at least one of the coefficients not 0 with one of the xi's not equal to 0. See, that's why I did this. This translates into a homogeneous system. I'll show it to you why. So now, so example, any three vectors in R2 are linearly dependent. So let V1 be equal to A11, A12, and V2 is equal to A21, A22, and V3 is equal to A31, A32. To show that they are linearly independent, we want to, so the question is, so is there a non-trivial solution to the equation x1 v1 plus x2 v2 plus x3 v3. Now, what is meant by okay? I'll translate. Zero vector means a vector with components 0 and 0. So let's write this out. This means x1 times a11 a12 plus x2 times a21 plus x3 times a31 a32. Okay, So what is the first component of this vector? Is it x1 times a11 plus x2 times a21 plus x3 times a31. This is the first component, and the second is x1 times a12 plus x2 times a22 plus x3 times a32. And what does this translate to? This translates to two homogeneous equations, right, in three variables. So this translates to two homogeneous equations. So this translates to two homogeneous equations in three variables. And by the basic theorem, this system will have a non-trivial solution. So by the basic theorem, this system has a non-trivial solution. Okay. So therefore, any three vectors in R2 are linearly dependent. And what would be the corresponding statement for R3? Any four vectors are linearly dependent, right? Okay. Now I have not told you what is so what is the definition of Rn? Does everyone know that? So let's now go to what is meant by Rn. And why do we say that its dimension is n? That's the main point, right? So, yes? Exactly, ordered n tuples. So, Rn is, no, let me write. This is set of all functions from the set 1 to n taking real values. Okay, and if f of I is equal to c is equal to xi or ci, we write f is equal to c1, c2 and cn. Okay, and how do you add functions? Like you do any other function. So when you add, you have two functions, f with components c1, cn and g with components d1 up to dn. Then what will be f plus g? Of course c1 plus n. And how do you multiply functions by scalars? As you do. Same thing translates here. Okay, and this is an example of a vector space over reals. If you change the real to some other thing, like do you know what's the field? Something in which you can add, multiply, divide, and so what other fields do you know? No, much earlier than that. Rational numbers,
Yes.
right? Then that if you look at all functions from 1 to n to rational, you would get qn. And if you look at all
Integers,
yes, it's close, but
dividing
you cannot divide.
Okay.
Yeah. Okay. They exist something like this. Okay, but I don't want to waste time on that. Okay. So So Rn is the main example of an n-dimensional vector space over reals. But I have not yet defined for you what is a dimension. Huh? So first of all, then what is a vector space? A vector space is something which mimics what you have in Rn. It's a set in which you can add elements, you can multiply them by scalars, and every element has its negative, right? Inverse or additive inverse, and that's a vector space. So do I need to formalize this, or is it clear now to you? It's clear, right? So a real vector space V is an abstraction of Rn. So technically it's a V has two operations, plus and multiplication. This is multiplication by scalars. Okay, and so addition is distributive. That V1 plus V2 plus V3 is equal to V1 plus V2 plus V3, right? And if lambda mu are scalars, then lambda mu times V is equal to lambda times mu V. Okay, and now come the vectors V1 up to Vk in V are linearly dependent if there is an equation x1 v1 plus xk vk is equal to 0, where xi are not all and then what would be linear independence? If you have any such relation, every xi must be 0. Okay, so example. So if then they are linearly dependent, if any such equation can only hold if all the xi's are 0. Linearly independent, sorry. Independent can only hold if all the xi's are must be 0. Okay. So for example, 1 1 and minus 1 1. Are they dependent or independent? How will you test it? आप दोनों component add करके और no.
Because the second component can be written in the form of first component.
Okay, no, I just gave you the definition. How do you check some vector? You have to write down the equation, right? So to check this, I mean for those who have been dealing with this, it's obvious, but for you maybe not. So linearly dependent or independent? This is the question. So the way to check is so let's look at. So you look at the equation. X1 times what vector do you take? 1 plus x2 times minus 1 1. So you want x1 minus x2. So this should be equal to 0 0. Let's see. So you want x1 minus x2 is equal to 0 and x1 x2 is equal to 0. So what is the solution of this? Both of them have to be 0. Okay. From here there are many ways to see it. Okay. So only holds only if x1 is 0 and x2. So then what's your conclusion?
Independent.
They are independent. So V1 and V2 are independent. And are 1 1 square root of 2 square root of 2. This is your V2. Are they dependent or independent? Huh? So how will we check this?
By scale factor of 2.
Yes, it's obvious, right? So clearly V2 is square root of 2 times V1. So square root of 2 times V1 minus V2 is 0, and we have a non-trivial solution. So these are independent. Okay, and then the next thing you have to know is
One can be expressed in terms of the other, then it should be linearly dependent, not independent.
did I write? What did I write?
No, you just said.
No, I said this clearly. So they are dependent. Yeah, this is what they are dependent. Yeah, because you have a non-trivial solution. It's obvious, right? Okay. So the next main idea you should know is the idea of a basis, right? So what is basis? Of a vector space over, I write this in bracket because this holds for any field, but you don't know what a field is. So for you, R can be instead of R, you can take the rational numbers or the complex numbers. Yes. Okay. So definition. V1 up to Vn is of a vector space V. V1 up to Vn is a basis if number 1 they are they are linearly independent. And number 2, every element of V, every element small v of V can be written as V is equal to C1 V1 plus C2 V2 plus Cn Vn, where Ci are okay, and we call this a technical word. We call this a linear combination of V1 up to Vn. Okay, and this is the theorem. Theorem. If V has a basis consisting of n elements, then every other basis also has, then every other basis also has n elements. Okay, so you already the main point you have already done, but I'll repeat it. So proof. Let V1 Vn, I'm using V for okay. Let V1 Vn and W1 Wm be two bases, right? Okay. So if they are different sizes, one of them has to be less than the other. Okay. So the main point is that if V1 up to Vk is the basis, then any set of, then every set containing any set W1 Wk plus 1, any not set, any sequence is linearly dependent. Right? This is was your homework. I spent a lot of time trying to convince you of this statement, right? So now suppose you have two bases of consisting of n and m vectors and m vectors. Okay, and suppose that n and m are different. So without loss of generality, we may suppose that n is less than m. So without loss of generality, we may suppose that n is less than m. So suppose that n is less than m. So we have bases V1 up to Vn and W1 Wn plus 1 Wm. Now, if I give you some linearly independent vectors, is any subset of them linearly independent? If I give you linearly independent vectors, then any subset of those is also linearly independent. Okay. So now W1 Wn plus 1 are linearly independent, right? But there are vectors in a space which has whose basis is V1 up to Vn. So is that possible? That's impossible, right? Now linearly independent, but as they are vectors in a space which is the basis of n elements. They must be linearly dependent. Okay, so this contradiction shows that m must be equal to n. And now we can talk about that. And this number, the number of elements in a basis, is by definition the dimension of the space. So the number of in a basis is called the dimension. Dimension of the vector space. Okay. Now Parvez was telling you yesterday about manifolds and their dimension. I think he is going to tell us a lot more, but if you look at why do we say so, you know, I'm going to do this in lecture tomorrow, tangent spaces and so on. But all of you know, if I give you a parabola, so what is a tangent? You know? So the dimension of the tangent line is 1 everywhere. Okay. So So in that sense, this is not absolutely correct, but this is one approximation. So in that sense, a parabola is one dimension, right? And because the tangent line has is of dimension 1, okay? And if I give you, most of you think so this is a sphere, right? So why do we say that its dimension is 2? We look at the tangent space. So what's the tangent space at this south pole? It is a vector space with dimension 2, right? So in that sense, that's a consequence of the definition. This is not true always that if something has dimension, there are counterexamples which you will see.
There's a simpler way to see this. You need 2 coordinates to locate a point.
Two coordinates to locate a point locally.
So that's
Yes.
the easier thing.
But, yes. No, I just want to relate it to what has this dimension got to do with the dimension of the manifold, right? Because we just discussed the dimension of vector spaces, and then the tangent spaces and so on, they come. Okay. Okay. Now why do we need spaces more than dimension 3, for example, right? So suppose I give you a disk and it is floating in space. So how will I specify its position?
Coordinates. You would define a coordinate system and then give us coordinates.
No, you put up a frame on the disk, right? So this is a disk, and you put a frame on it. And this is the center, right? And after some time, this is somewhere here, and the center is this, but it has rotated by some. This was the original orientation. It has rotated by angle theta. So how many coordinates do you need? 3 for the center and 1 for the orientation. So you need 3. So this state space is needs 3 variables, right? And what about if I have a ball floating in space? How will I specify it? I will specify it by center. Center has how many coordinates? 3. And then you have how the frame is rotated. Those are called the Euler angles. So you have 3 for this, and then you have in total you have 6, right? So already there. But even more in mathematics, it's very important to have higher dimensional space. For example, you look at Pn. These are all polynomials of degree less than equal to n. So how does an element look like here? A0 plus A1x plus ANxn. So what would be a basis of this space? No, what is it?
X square.
What about A0? 1. 1 x up to xn. So basis is 1 x xn. And why is it a basis? Because if you take a if you take a linear combination and you set it equal to 0, it should be 0 for all x. So this means every coefficient has to be 0, right? So this is a basis, and it's a vector space of dimension n plus 1. Okay, and now Dr. Waqas will teach you Sturm-Liouville theory. One approach to that is through linear algebra. You look at operators like 1 minus x square. Doctor, is he here? What's the other thing? Plus x times I prime or what? For the Liouville.
Yeah, so it's
1 minus x square y double prime plus
2xy dash.
plus 2xy dash. Now when you calculate this, I'm jumping, but this is an operator. When you calculate, it will have distinct eigenvalues, and it will have so it will have a basis of eigenvector, and those are the Liouville. So already thinking about polynomials as vectors pays you.
This is not the general Sturm.
Yeah, exactly.
No.
It's d by dx of p of x dy by dx plus r.
जी, but this is the one
Legend's differential equation ये minus होना चाहिए वैसे minus.
चले माइनस मुझे याद नहीं जी
क्योंकि derivative में लिखा है ना exactly.
जी तो ठीक है जी so in that context it is also useful. Okay, I have still half an hour. Oh, but I'm finished with the material, so I will just improvise. Okay. So, huh?
You have 35 minutes.
35 minutes. Okay. So,
I think 7-8 minutes earlier.
huh?
Started 7 to 8 minutes earlier than
Really?
yeah,
So
so
you want me to finish earlier?
half an hour is good. Yeah, half an hour, you still have half an hour.
Okay. Ji Parvez, you have some question?
Just thinking that the simplest 6-dimensional space would be you take a particle's position x, y, z, and then it's also moving, so momentum px, py, pz. You combine these together in one point, which is called phase space, and that's a 6-dimensional space for one particle. For n particles, it is 6n dimensional. So in statistical mechanics, you deal with spaces of billions, trillions.
But Parvez, the problem is that they have never seen a particle. So they have seen a ball floating. So that's why I gave the example of a ball. Okay. So now Parvez said that I have not explained to you what a group is, right? So
I didn't say that, but you have not.
I have not. Okay. So we look. The best example of a group is the group of permutations. Okay. So what's a group? It's a set together with the product defined, which should satisfy an associative law, and every element should have inverse. So let's look at so best example is permutation. Okay. So first of all, if S is any set, and f is a function from S to S, and g is a function also from S to S, and h is a function from S to S. So is it true that f composed with g composed with h is equal to f composed with? This is true for any functions. Okay. Now we specialize to what is a permutation. It's a one-to-one map, and it should be onto. So a permutation is one to one and onto. A permutation of S is one to one or onto, but S can be anything you like, right? For example, your set S could be R2, right? And what's a linear transformation? A linear transformation is just a linear function, but we are considering at the moment homogeneous. So let me give you an example. So what is, so main example is GL2R. These are all linear transformations. XY goes to let's say A, B, C, D, XY, where this determinant which is AD minus BC is not 0. Okay.
So what is GL?
GL2, is a set of all linear transformations with a non-zero determinant. General linear. And SL, special linear, is determinant is equal to 1. That's SL. Okay. And now so whatever I am going to do, this generalizes in for any n, but let's see. So you define, SL2R is set of all A, B, C, D such that AD minus BC is equal to 1. Okay. So it doesn't, yeah.
Sir, what's the difference between a group and a set?
Uh,
Let's say a set of all linear transformations.
Sorry. What the set of all linear transformations which are invertible, which are non-singular, which are invertible.
Yes.
I think you need to put down the group assumption.
Okay, let me. So, so you are saying what is a group and what is a set?
Yes, the difference.
If you are a philosopher, any set can be a group. Do you know why? Because you can always have a one-to-one mapping from any set to any other group, and then it becomes a. But anyway, I'll give a formal definition. Okay, so a group, we have enough time. A group is a non-empty set. Set together with an operation let's mu from a group G, from G cross G to G, which satisfies the following. These axioms. Okay, so okay, so writing mu xy as x circle y, we have number 1 x circle y circle z is equal to x circle, okay, and 2 every element has an inverse written x inverse, so that there is an identity element E such that this E is of course not is not 2 point whatever. This is E is shorthand for element. Okay, so identity element E such that x circle E is equal to E circle x is equal to x, and 3 every element x has an inverse written x to the minus 1 with x composed with x minus 1 equal to E. And it's, I don't want to get into axiomatics. X composed with x inverse is the same as x inverse composed with x. Okay, so this is a group. Okay, and what is the main example? As I told you right at the beginning, set of all permutations. So main example is set of all permutations. Second, all invertible linear transformations. Of Rn. So this is called GLNR. And with determinant 1, it is called SLNR. So,
Can I ask you a question?
Sure.
I'm not familiar with the whole subject, but this has been used by the particle physicists.
Yes.
So, what gave them an idea that they can actually classify the particles in terms of groups?
This is something about which I don't know anything myself.
Maybe Professor, I can ask you, Gell-Mann problem was the first one who actually introduced the idea, or it was much before him?
Wigner.
Wigner, okay.
I think Wigner gave that theory.
But do we have any idea, I mean, what made them think that way?
The particle are irreducible representation of point car group. So वो point car group
Long before that was Wigner,
Yes.
and he said the Hamiltonian has got symmetries.
Yes.
There are under certain group operations. So, for example, inversion or rotation, and so the eigenfunctions of the Hamiltonian can then be classified into certain representations, irreducible representations, and then the whole thing goes off from there.
Irreducible representation.
But I think
अगर मुझे
here
layman को
we are
समझाएं।
still not clear. Hassan is giving us examples of groups and so on.
जी, but I think Parvez is a better person to ask this question. जी. Okay, so okay, so GL2R. So this is all functions of the form xy goes to a, b, c, d, xy, or x is equal to ax plus by, x goes to, so f of xy, this is ax plus by, and cx plus dy, okay? And you can check that the composition of two such is again a linear function. So, when is this invertible? If the determinant is not 0. And if you assume that the determinant is 1, it is SO2R, okay? So it is, sorry, it is SL2R, not SO2R, okay. So determinant is 1, then it is this is SL2R. Okay, and there's nothing special about 2. The same thing makes sense for any n dimension. You have GLNR and SONR. Okay, and now the other thing was SO3R, right? In the, so what is, okay, so you put on R3, you put a an so-called inner product xy b of this is xyz uvw is equal to xyz times uvw. And what is this? What's the dot product? It's a xu plus yv plus xu plus yv plus zw, right? So let's just to save time, we write bxy b. So if v has component x1, x2, x3, and oh, I should stick to this. And W has components, no, I can't use V1 as this, and V2 has components UV, UVW. Then B of V1, V2 is equal to V1 transpose times V2, right? And a transformation is orthogonal if transformation, a linear transformation. A linear transformation T is orthogonal if B of V1 V2 is equal to B of T V1 T V2. Okay. So this translates to if the matrix of if T is given by T of x y z is the matrix A times x y z, then T is orthogonal if and only if A times A transpose is the identity matrix. What is the identity matrix? It is a matrix which has only ones on the diagonal and zero otherwise. Okay. Now there is so this is so you get O3 it's clear it. So this is orthogonal group, and from here if you see A times A transpose is identity. Do you know determinant of A and determinant of A transpose are the same?
Yes.
This is one fact, right? So this means determinant of A square has to be 1. So determinant of A is 1 or minus 1. The matrices of determinant minus 1 do not form a group, right? Because when you multiply two matrices of determinant minus 1, the product will be plus 1, okay? But the matrices of determinant plus 1, they form a group. So SO3 is SO3, all elements of O3 with determinant okay. No, minus 1 कैसे? You take an element of determinant minus 1, take two elements. Determinant of A is minus 1, determinant of B is minus 1. What is determinant of A times B? So is it a group? Discrete से कोई ताल्लुक नहीं. Group का मतलब ये it's a set. If you take any element A and B, then the product of A and B should be in that same set. Okay. So you are right that if you, these are all linear, all transformations with determinant minus 1. Of course, they are all invertible linear transformations, but those of determinant minus 1 do not form a group, right? So the full orthogonal group contains one subgroup, which is the special SO3, and then you have other elements, okay, and you just need one element to generate the whole. So those with determinant minus 1 are called reflections, okay. So you can prove that their reflection का क्या मतलब है? It's a linear transformation which fixes the hyperplane and sets a perpendicular vector to its negative. So that's a reflection. So this you can, okay. And then the other term was, you see here I had A times, I had B V1 V2 is equal to V1 transpose V2, right? But I could take another one. V1 transpose So so what was it? Yeah, I had A times A transpose is equal to identity, right? But I could define any scalar product not necessarily positive definite. For example, I could define x1, x2, x3 dot y1, y2, y3 is equal to x1, y1 plus x2, y2 minus x3, y3. Okay. So, and if you compute, so the which preserves this is SO21. Okay. So the
How do you do that? But the minus के लिए आमतौर पर तो you need to have some imaginary thing to.
no. You not at all. I mean, let's be even more simpler. Let's go to 2 dimensions. xy dot x2 y2 is equal to x1 x2 minus y1 y2, right? This is a good old, this is an inner product, right? You are right. If you go to the complexes, then you can multiply then over the complexes everything will be equal to the standard inner product. Okay.
This is just how you have chosen to define it.
Yes, exactly. I am saying that but the group you get would be so the isometric group here would be. No, that's a positive definite inner product. Okay. Here you have to take. I agree. You have to talk about it should be non-degenerate. Means that a vector which is perpendicular to every vector has to be the 0 vector. So positive definiteness you replace by the non-degeneracy. Okay. So the isometric group is O11, okay, and SO11. This is all matrices cos theta, sin theta, cos theta. For SO2 they are this is a set of all cos theta, sin theta, minus sin theta and cos theta. Does everyone know what is cos? What is it? Huh?
Hyperbolic geometry.
No, forget about geometry. What is the definition of cos theta?
E to the power x plus e minus e to the power minus x divided by 2.
There's no x is theta.
So e raised to power theta plus e raised to power minus theta divided.
Yes, yes. Cos theta is e to the theta plus e to the minus theta divided by 2, and e to the theta minus, right? And in terms of exponential, what is cosine? E to the I theta plus e to the minus I theta by 2. Okay, so okay, so so what about SO? What was the other? I said SO21. SO21 would be what? It's the all 3 by 3 matrices, all 3 by 3 transformations of determinant 1, which preserve the bilinear form x y z dot UVW is equal to XU plus YV minus ZW. Okay, and we'll figure out when we go along. But you know, this was completely improvised. I didn't know that I would finish in such an early time.
हम यहाँ पर मैट्रिक का देना 1 और -1 करोगे तो ये मसला वो जो हमारे माइंड में था वो हल हो जाएगा।
कैसे क्या कह रहे हैं?
मैट्रिक अगर हम
नहीं, अच्छा, मैं समझ गया. So if I give you any matrix B, n by n, okay, you can look at all matrices A such that A B A transpose is equal to B, right? Now you can check that all matrices, okay. यहाँ से क्या हमें आता है? What is determinant of A?
डिटरमिनेंट ऑफ x प्लस -1
No. Determinant of A times determinant of A square times the determinant of B is equal to determinant of B. So if determinant of B is not 0, determinant of A square has to be 1. So let's assume that B is non-singular. So assume B is non-singular. Determinant of B is not 0. Right? So this is a group called OB, the orthogonal group corresponding to this matrix B. Now it's up to you. You can take B whatever you like. Normally we take it to be identity or with plus ones and minus one. If you take P of them plus 1 and Q of them minus 1, we get O P Q.
Sir, sign will decide that what we should write, sine or cosine. If sine is
No, this has got nothing. Sine and cosine are general. If you take B is equal to 1, 1, 1, right? So the corresponding group you will get will be O of 3. And SO3 means determinant is equal to 1. If you take B 1, 1 minus 1, you'd get SO2 1. No, you get O2 1. And SO2 means determinant has to be 1. We know the determinant has to be plus 1 or minus 1. And and this is important in physics. If you take B equal to 1, 1, 1 and minus 1, right? Then this is called O3, 3, 1. Okay. Now comes your question about cosine or sine. Okay. This may not make much sense to you, but okay. Okay. So this group is generated by this gives you a copy of SO2, right? Then here this gives you a copy of SO2 and this gives you a copy of SO11, right? So it's generated by 2 SO2s and 1 SO11, or it could be generated by SO3 and by O3 and O11 of determinant 1. But this will not make sense to you why it is true. I am just telling you that we will show this eventually. Okay. Any other question?
Sir, can you quickly explain the notation that you're using to write the groups like SO, what each letter means, or like, you know, when you're using 2 numbers in the brackets as opposed to 1?
Oh,
just the
sure. This is 2 by 2 matrices, right? This is A, B, C, D such that A, B, C, D times, what is the transpose of this matrix? A, B, C, D. This should be equal to 1, 0, 0, 1. Okay? Now if you figure out, so A, B, C, D is the inverse of this, and you know how to compute inverse. If you figure it out, if you assume that determinant is 1, so this implies that you can solve for them and you will get A, B, C, D is equal to cos theta A, B, C, D is equal to this, right? Does it answer your question?
So the first number in the bracket corresponds to the dimensionality of the matrix. Like if it's 2,
That's
then
right.
it's 2 by
That's
2.
right. That's right.
And then SO represents.
O represents the orthogonal. So if I give you A is a 3 by 3 matrix, right? And A times A transpose is identity. Then this will be an element of O3R. So this implies, this is the definition, A is in O3R, right? And if I say that its determinant is 1, then it will be in SO3R. Determinant is 1. Okay. And now since we are in it, why not SU2? So what is SU2? नहीं उसकी definition भी तो कोई होनी चाहिए ना. So SU2 is, so U2. You take, so U2, हाँ आप बताएं अब size क्या होना चाहिए? 2. A is a 2 by 2 matrix. and A times A transpose, if I say identity, it will be orthogonal, but no, I have to put the conjugate. If you put the conjugate, then this is U2, and SU2 means determinant 1 and in U2. Okay. Then what would be SU3 or what will be U3? 3 by 3 matrix, so that A times A bar transpose is identity. Okay. That will be your U3. And if you say it is SU3, the determinant has to be 1. Clear? Is it, we have more time or?
We are done now. Time is up.
Time is up. Alhamdulillah.